In that last video, I made a comment about vectors, saying that I had referred to them before. Looking back, I'm not sure that that's true. So let's take a minute and talk about vectors and phasors. I'm quite sure I haven't talked about them before. And let's figure out what this is. Okay, so vectors, and it's weird. I've been looking back through the notes and I feel like we've talked about vectors, but I just can't see anything that says that I have. So let's start at the beginning. What is a vector? A vector is a straight line. It's a straight line. It is drawn to scale. Although I will apologize because I'm going to be doing everything freehand, so don't hold me to that. I will, to a certain extent, I'll try. It's a straight line drawn to scale with direction and magnitude. Okay, so there's what a vector is. It's a straight line drawn to scale with direction and magnitude. Okay, so it has meaning. Okay, and we can draw a vector to represent anything. Okay, so if this is Kingston and this is Ottawa, I can draw a vector and say that to get from Kingston to Ottawa, it's, I don't even know the kilometers, it's about an hour and a half drive in a northeasterly direction. Okay, I could draw Toronto down here, and I could say that it's a 2-hour drive in a roughly westerly direction. Okay, those are vectors. All right, they have meaning in both the length of the line and in the direction of the line. Okay, and so that's obviously expressed with this arrow, but it's also in terms of its orientation. Okay, what does that have to do with electricity? So of course everything has to tie back to some electrical conversation. And well, let's talk about the direction a little bit more before we go there. Okay, I've already mentioned this as well. You saw this in the one video that the horizontal line to the right is what we call 0 degrees. Okay, and as we travel in a counterclockwise direction, the angle increases. And so this here at the north is 90 degrees. Okay, now what I'm referring to here, so let's go back to the right angle triangle because that's what this is all about. Okay, if we were to draw a right angle triangle right here, okay, there's the right angle triangle. You're saying, well, that didn't look much like a right angle triangle. It does now. There's the right angle, and there is the angle theta. Okay, but where we're going to go with this now is that there's the vector. Okay, so the vector in this right angle triangle is the hypotenuse. Okay, let me take a different color and I'll draw a different vector. So let's put it there. Okay, now here is our right angle triangle. Okay, we now have a different angle. Okay, see how that angle theta is a larger angle than the original green one, and the hypotenuse is much longer, so we have more magnitude in our vector. Okay, kind of coming out about this in many different ways. But then when I showed you the trigonometric functions, the sine wave and the cos, and we know it makes sense to talk about the angle within the first 90 degrees. We can draw and we can see that right angle triangle. But we can actually go well beyond that. Beyond the 90 degrees, we can come over here to 180 degrees. Okay, and grab a different color. I could draw the vector over here. Okay, now we have a couple of different things going on. I could draw the right angle triangle right here. And we have an angle theta right there. Okay, but we can also do the math on this angle around here. Now it becomes nonsensical when we think we're talking about a right angle triangle, because we can't possibly create a triangle with that angle. Okay, but that angle is 180 degrees minus this angle in here that creates the right angle triangle that makes sense to us. Okay, so because of the sine wave, we get repetitions in values. Okay, so let's just draw the sine wave here for a second. And it carries on beyond that. But there's 90 degrees. There's 90 degrees. And we actually get the same value. Remember, if this is a sine wave, this is 0 and this is 1. It peaks at 1. Okay, if we look at, say, 0.8, okay, 0.8 exists. Actually, maybe that's 0.7. I don't know. Sorry. Having trouble with the drawing to scale. But we get this value when we calculate the sine at this angle. But we also get that same answer over here at this angle. And so what happens is we can calculate this interior angle that makes sense to us. Or we can calculate this large angle out here, which is greater than 80 degrees. But we actually get the same answer. We end up with the same number. Okay? Now, when we move beyond the 180 degrees, okay, the same is true down here, sort of. Okay, we can come down here and draw a vector, and we can work with this angle, or we can work with this angle. Okay, and so now it's 180 degrees plus the additional angle. Okay, and down here we can come up with the same absolute value, but now it's negative. Okay, so mathematically, we can do all kinds of crazy stuff with vectors. And the point is, getting back to the conversation, the vector is the hypotenuse of all of these right angle triangles that we keep drawing. Okay, now, the question is why? And the answer is, what shall I erase? Let's erase all of it. The answer is, remember the second half of the term, this is all about solving AC. And an AC power supply comes back to this sine wave. There it is again. But the point is that it's always changing. Okay? And we have to do math on that. And that gets very complicated. Okay? I know when I introduced vectors, we did this in three-phase, right? I hope so. Okay, that's pretty complicated. But if we replace that with a vector, okay, that's a lot easier to work with. Okay? In a three-phase system, if we have another sine wave here, well, now it's getting really complicated. But I know that this sine wave is 120 degrees beyond that sine wave after. And so, in fact, after is back this way. So I could draw that red vector there. And I can tell you that this is 0 degrees and this is 120 degrees. And so this angle here is 120 degrees. Okay, we can draw one more sine wave. It's going to go there, and it's going to go there. And we have another 120 degrees there. That's actually 120 degrees because this is located at 240. And so we have 120 degrees there and 120 degrees there. Okay, so this is much tidier and much easier to work with, and we can do some math on this fairly straightforward as opposed to trying to make sense of this. Okay, and so that's the reason that we move on from our sine wave to use a vector to represent an AC circuit. Okay? Now, what's this thing called phasors? Well, a phasor is kind of a made-up thing that we as electricians use. Okay? It is just a vector. So what is a phasor? A phasor is simply a vector. Used to show electrical phase relations. Phase relations. Okay, so that previous three phases that I just drew to show the three-phase power in vectors instead of in the sine waves, while they are definitely vectors, specifically they are phasors. So we are using vectors to show a phase relationship, to show how one sine wave lags behind another sine wave by 120 degrees. And we can show two vectors separated by a 120 degree angle to represent that phase relationship. Okay, so when we're throwing out these terms of phasors and vectors, that's what we're talking about. Now, I probably won't use the term phasor a lot. Okay, we'll recognize it for what it is, but I'll probably just end up calling them vectors. Okay, because that's what they are. Okay, but they are specific vectors. We are using them within the electrical field to represent phases. One final detail that I better include, this is an important one, okay, and this is, I mean, I will probably end up saying this is about vectors, but I suppose specifically this is definitely about phasors, specifically when we're talking about vectors representing electricity, okay, we can use vectors to represent voltage, and we can use vectors or phasors to represent current. We want to be able to tell them apart at a glance. Okay, and so here's how we do it. When we draw a vector or a phasor representing the voltage in our circuit, we will do so using an arrow that looks like that. When we're talking about current, we will use an arrowhead that is closed in. Okay, so we will draw our vectors or our phasors a little bit differently so that we can tell at a glance whether we're talking about voltage or whether we're talking about current.